Hello, this is Jack Jackson. Let's take a look at some triple integrals in spherical coordinates. So let's start by reminding ourselves a little bit about spherical coordinates. Rectangular coordinates, we have x, y, and z. Cylindrical coordinates, we have r, theta, and z. And spherical coordinates, we have rho, theta, and phi. Sometimes this is called phi or phi. So anyway, what are these things here? Well, of course, x, y, and z is you go out on the x-axis a certain amount, then in the y direction, then up z to find the point. For the cylindrical, you start by going out a distance r, it's purple distance, and rotate by an angle theta, which is this angle here that this line here makes with the positive part of the x-axis. So theta is this amount of rotation here. And then you just go up z. But now in spherical coordinates, you go up the z-axis, the distance rho, rotate that down along the x-axis, toward the x-axis by an angle of phi, and then rotate that in theta. So theta is still going to be the same, but rho is going to be the distance from the origin to that point. These black distances are actually the same. The angle we're looking at, it's why they don't look quite the same. Now if you'll notice that phi is then this angle that the z-axis makes with, the positive part of the z-axis that is, makes with this line segment going from the origin out to our point. Now we have some relationships that are really given completely by these two right triangles. This right triangle here relates x, y, r, and theta. So x squared plus y squared equals r squared from the Pythagorean Theorem. That's right here. And then you get your basic trig relationships, right? The cosine of theta is x over r, the sine of theta is y over r, and the tangent of theta is y over x. And so that gives you all you need to go between polar and rectangular coordinates in 2 dimensions, or rectangular and cylindrical coordinates in 3 dimensions. Of course, z is just z. Then we look at this right triangle here, which shares a side with this other right triangle. So this one is setting up in 3 dimensions. This one's laying down on the xy plane in 3 dimensions. But they're both right triangles. But the difference is this purple side here, r, is its length. It is the hypotenuse of the triangle down here with x, y, and r for the sides. But it's one of the legs up here on this one here, where the sides are length r, z, and rho. And so you get r squared plus z squared equals rho squared. And of course, r squared is x squared plus y squared, so you get x squared plus y squared plus z squared equals rho squared. And then phi is this angle right here, but because of this green piece here being parallel to the z-axis, we get what's called the z property that says that alternate interior angles formed by transversal, that's this guy here, to a pair of parallel lines here, these two angles then must be congruent to each other. So this is also an angle of size phi right here inside this triangle. So again, here you have a right triangle, here you have a right triangle. Everything is contained in those right triangles if you just remember the Pythagorean Theorem and the basic trig functions. So for example, again, the Pythagorean Theorem, r squared plus z squared equals rho squared. And then x squared plus y squared equals r squared gives you these two equations at the bottom here. From the little triangle on the floor, cosine theta is x over r, sine theta is y over r, tangent theta is y over x. Now from this triangle here that's standing up, we get cosine of phi is z over rho, and sine of phi is r over rho. Okay? And so now we see that. Now let me show this for just a second. Okay, so we can look at it in this picture here, and I can move this around a little bit so you can see things maybe a little bit better. Here you can see the triangle on the floor, which is a right triangle. With theta here, usually we orient it this way. Okay, and then here you can see the one looking straight on this way, almost. And so we can see that right triangle that way. You can also see that these are actually the same length. Get right on it there. Yeah, now you can see that a little bit better. Get right on that thing. Where these are the same length there, you can see these two angles are the same size. So you can kind of see a little bit by moving this around, you can get a better picture of the 3D nature of what's going on. Okay, so hopefully that helps a little bit looking at that. Now really, again, all you really need to know is to see those two triangles and everything is contained there. But then here are the basic key relationships here. And over here is one way to get these to change from one coordinate system to the other two. And these specifically use a positive r and a positive rho. And specifically I've chosen a theta between minus pi over 2 and positive 3 pi over 2. Although there are certainly other choices for theta. Phi is almost always given as an angle between 0 and pi. So in any event, here's what we can do. If you have x, y, and z, r is the square root of x squared plus y squared. And theta, well, tangent of theta is y over x. So it's just the arctangent of y over x when x is positive will give you theta. When x is negative, you get the arctangent of y over x, and then you have to add pi to that. And, of course, if x is 0, these are undefined. So if x is 0 and y is positive, the angle theta is pi over 2. And if x is 0 and y is negative, the angle is minus pi over 2. So that's one way to get a specific value of theta, and that always turns out to be in that particular interval there. Rho, then, if you're going to spherical coordinates, is the square root of x squared plus y squared plus z squared. And phi is the inverse cosine of z over rho, which we get from this cosine of phi is z over rho. Of course, rho is just the square root of x squared plus y squared plus z squared. So the arc cosine of z over the square root of x squared plus y squared plus z squared, that is how you could get phi, or phi if you prefer that pronunciation. And here we go, r, theta, and z. If we're starting with that, x equals r cosine of theta, y equals r sine of theta. Rho is the square root of r squared plus z squared. Phi, again, is the inverse cosine of z over rho, so that's the inverse cosine of z over square root of r squared plus z squared. So these show you how you can take your r, theta, and z and get x, y, rho, and phi. The last one here is if you have spherical coordinates, rho, theta, and phi, we get r is rho sine of phi, x is rho sine of phi times cosine of theta, because it's just r cosine theta. So see how can we just substitute that in. Y is r sine of theta, so it's just rho sine of phi times sine of theta. And from this one here, we see that z is rho cosine of phi, and so we can see that expression there. So we can see how to convert coordinates from these different coordinate systems. We've kind of looked at this before. That was a little bit of a review. Now we need to figure out what we have to do for the differential dv. Now remember, we can use those formulas back here on this page here to convert the formulas for the integrand, and we can use those to convert the formulas for the limits on our integrals, you know, among the different systems, converting among them. But we also have to keep track of how we convert that dv. Okay, for example, we knew that dv was dx, dy, dz in rectangular, but it was r dr, d theta, dz in cylindrical. So what is it going to turn out to be in spherical? And the key is to look at this little slice here. So we're going to slice things up. In rectangular coordinates, the slices turn up to be little rectangular boxes. So you slice it with x equals a constant, y equals constant, z equals constant, and you end up with these little boxes that are right rectangular prisms. And of course, we had a certain shape that we got when we sliced up with cylinders. When we slice with constant thetas, we get a radial slices out from the origin. Constant r's give us circular slices, and constant z's give us horizontal planes. And then they gave us a little shape that was, a piece like a sector of an annulus of a circle, like a sector of a washer, and then with the constant height. That was what we had for the cylindrical. Now, what do we have for spherical here? Well, if we slice with constant rho, we get spherical pieces. We get rho equals a constant sphere. So this surface on the outside here and on the inside here are parts of spheres. Then if we slice it with theta equals a constant, we're slicing flat here on this side and this side with planes. So this side over here and this side over here are portions of planes. If we slice with, and then see what happens now when we go with phi as a constant. Well, phi as a constant is a cone. So we have how this intersects with a cone is with little circular pieces here. So actually all of these pieces are arcs of some kinds of circles except for these four. This one, the green one, and this one here, this one here, and this one here. Those are just straight line segments. So that one is just a straight out delta rho for a line segment length. Now this, let's do the purple one next. So if you look at this purple length, that's just a slice of a circle of radius, constant radius rho, but it's only going from an angle of delta phi. Remember, phi is the angle across here as you rotate out from the z-axis. We rotate here by a certain amount, we rotate even further to get down here. The difference in those rotations is an angle down here between, say, that line and that line, that rotation. Okay, and that is going to give us just rho times delta phi for that length. And then if we look at the red length here, that's going to be where we have a cone coming out. If you have a cone coming out, it's a constant radius. So it's a constant radius r, and then it's sliced off by this delta theta being the angle between, say, that line and that one here, between that ray and that ray. And so it's going to be r delta theta. But r, again, is rho sine phi, so it would be rho sine phi delta theta. And roughly speaking, this box that you have here, it's not a rectangular box. It's got this, whatever shape this is. And we multiply these basically together to get that. So the volume is approximately a delta rho times a delta phi and a delta theta, but we also have a rho times a rho and a sine of phi. So it's approximately rho square sine phi delta rho delta theta and times delta phi. Now, more properly speaking, this is closer to being correct when you have a point in the middle somewhere, and r or rho is the distance out to that point. And at that point, go from sort of side to side of the box here, kind of like we did this one here, and then use for that one and that angle for phi coming down. Use that. And then similarly, at a similar point or same point, we do this one here instead of the purple one here. We do that, and that's more or less that rho times the delta phi. And that's going to be closer to the correct thing. It's actually a little more complicated to actually set this up, and chase through the geometry of everything. But so we'll formally derive this and verify that this is correct using a technique that makes use of Jacobians for transformation of coordinate systems. We'll look at that in our next section, and one of the things that we'll do is make sure that we prove this formally. But in any event, this is correct. And so when we take the appropriate limits, it basically turns out just fine, so that dv equals rho squared times sine of phi times d rho d theta d phi. So here's this same thing, just to have a better look at the box here, so that you get a better view of it. Okay. If we're looking from above, we've got a cone coming out here, slicing this. If you're looking from this way, you can see the different surfaces from the sides there. So hopefully moving this around gives you a little bit better feel for what that thing looks like. Okay, but at least as an approximation, that is roughly delta rho. That side's roughly rho delta phi. This is r delta theta, or rho sine phi delta theta. So in any event, we get dv is rho squared sine of phi d rho d theta d phi. So we see that this differential for the volume dv is dx times dy times dz. That's for rectangular coordinates. For polar coordinates, that changes to r, dr, d theta, dz for cylindrical coordinates. For spherical coordinates, that becomes rho squared sine of phi d rho d theta d phi. Now, when you're doing this, when you're setting up an integral, for example, make sure that you include all of the parts that need to be there. For example, if it starts out with dx, dy, dz, and you convert it to cylindrical coordinates, you'll get dr, d theta, dz in some order, but don't forget to put the r in there. And similarly, when we're going to spherical coordinates, you'll get a d rho, d theta, and d phi in some order, but don't forget that you need a rho square and a sine of phi. All of that, everything here is part of that dv, just like everything here and everything here is part of the dv. Also remember that you have 6 different orders here of the dx, dy, dz. There's 6 possible orders there, 6 possible orders here and here as well in both cylindrical and spherical coordinates. And depending on which order you pick depends on what the shape looks like that you're integrating over, how that's going to be more easily set up in terms of figuring out your limits. So remember, when you're setting up your integral, that you have to get the integrand set up in the right coordinate system. You have to get your limits on all 3 integrals set up in the right coordinate systems. And then you also have to get the dv correct. So be sure that you don't forget that part of it. Okay, so let's take a look at an example. Suppose we want to compute the mass of a solid which has density delta of x, y, z is x squared plus y squared plus z squared. And the solid is bounded above by x squared plus y squared plus z squared equals 4. And below by z equals the square root of x squared plus y squared. So we have 2 surfaces there, and we're talking about the region in between them. And then we have a density function. But if you'll notice, these are all given in x, y, z coordinates, or rectangular coordinates, but the integrand and the surfaces are better described in spherical coordinates. Hopefully you can look at this and just see, oh, that's just a rho square here for x squared plus y squared plus z squared. Hey, there's another rho square. Hey, and that's a square root of an r square, so that's just r. And we could change that to spherical pretty easily as well. So let's take a look at that. So we have delta is x squared plus y squared plus z squared. Well, that's just rho squared. So that's a nice, easy function in terms of spherical coordinates. quite a bit simplified from what it would be in rectangular coordinates. Anytime you can get rid of square roots, that's kind of nice too. So z is the square root of x squared plus y squared. Well, square root of x squared plus y squared is r, but r is rho sine of phi, and z is rho cosine of phi. Well, wait a minute. If we divide both sides by rho, we get cosine of phi equals sine of phi. Divide both sides by cosine of phi, we get sine phi over cosine phi is 1, or tangent phi is 1. Well, wait a minute. If tangent phi is 1, and remember, phi is going to always run from 0 to 2 pi somewhere in general. Or 0 to pi anyway. In fact, here it's going to be between 0 and 2 pi, 0 and pi over 2, because z is a positive number. Okay, and so what do we get? Well, we get a constant here. If the tangent of phi is 1, then phi has to be pi over 4 with those conditions. And we can choose it so that rho is a positive number. So we got our positive number for rho. We've got a phi is constant for this surface on the bottom. So that's just a cone. We have the surface on the top, x squared plus y squared plus z squared equals 4. Well, that's just rho squared equals 4, and we can choose a positive rho. So that makes rho 2, that's just a sphere. So the top is a part of a sphere. The bottom is part of a cone. This thing looks kind of like an ice cream cone. This angle with the x-axis is pi over 4. Pi over 4 on this side. And the top is a sphere. Let's take a look at this a little bit more in where I can manipulate the figure. So here you can see the graph as surfaces, and moving this around a little bit can help us see what's going on. So you can see the sphere on the top, or part of a sphere. On the bottom you see part of a cone. So this thing looks kind of like an ice cream cone. Okay, so if we look at it from the side here, we can see the angle of pi over 4 here. Okay, and pi over 4 on this side, so the angle between these is a right angle. So you have a right angle at the bottom here. And let's see what else. If we look at it this way, you can see the intersection is going to be this circle here for the two surfaces. We'll talk about what circle that is here in just a minute, but notice it's a circle where z is a constant. We look on it straight from the sides. And hopefully, anyway, looking at that from some different angles there can help you get an idea of what that looks like a little bit better. You may notice on the sides here I have parametric equations for that circle where they intersect and the surfaces, and you might look at these to see what they are, but we're going to examine that here in just a minute. So, looking at this a little bit more closely, let's see, this is what we have here. So notice it turns out that the density function is actually a real simple function. Density is rho square. And actually we have constant functions for the surfaces. The top is a sphere, rho equals 2, and the bottom is just a cone, phi equals pi over 4. So that's about as simple as you could possibly get it for the describing of surfaces if you have constants. Now let's look at quickly at this intersection. I've said that this is a circle. So let's see if I can show you how this works. We have x squared plus y squared plus z squared equals 4 on the top, and x squared plus y squared equals z squared on the bottom. I got that by squaring both sides here. If we substitute in, x squared plus y squared is r squared, but then r squared is also z squared, so the z squared is r squared, this part is r squared. We've got 2r squared equals 4. That says r squared equals 2, so r is the square root of 2. So that circle that we see there, it has a radius of square root of 2, and you can see that it's at a place where z, if you plug back in, is the same as r. Right? So z squared equals r squared. Z and r are both the same. So z is the square root of 2. So this is at a height of square root of 2 and a radius of square root of 2 is that circle there. Okay, that may come in handy for us to notice that. Now to graph this in the graphing software, I used GeoGebra. I needed to, or one way I could do it at least, was to enter it as parametric equations. So remember, the top sphere is x equals, well, always x equals rho sine phi cosine theta, y is rho sine phi sine theta, and z is rho cosine of phi. Now we just put in our formulas for that. For the top sphere, rho is a constant, is 2. So in fact, all of these, I'm going to just replace rho by 2. And now you see that we have a surface defined in terms of two parameters, theta and phi. If you looked quickly at the screen before, when I had the software up, I used u and v for those parameters. But it doesn't matter what we call them, they still represent what we're calling theta and phi. And what limits do we have on these? Well, it goes all the way around the circle this way for r, so for theta, so it goes from 0 to 2 pi. But phi only starts at the top, 0, and rotates out to here, which is pi over 4 everywhere. So it goes from 0 to pi over 4. Okay. For the bottom cone, we have the same formulas for x, y, and z, but now we have to substitute in. Well, we substitute in phi as a constant of pi over 4, and the sine and cosine of phi are both 1 over the square root of 2. So I just replace all of those by 1 over square root of 2, and we have our equations here. And now we have our two parameters, which are rho and theta, producing the surface, which is that cone. The rho is going to go from 0 out to 2. Okay. And then so that's for this surface here. Remember, so sometimes the rho is 0, sometimes it goes all the way out till it hits the sphere, which is 2 in radius. And again, it goes all the way around for theta, so theta goes from 0 to 2 pi. Now that should help us to set up our integral. So let's set up the integral now. The mass is just the integral of the density function delta dv integrating over the domain. Okay, and I chose to do rho, then theta, rho, then phi, then theta. So our delta function is just rho squared, so we put that there. dv, remember, we spent some time developing this, is rho squared sine phi d rho d theta d phi in some order. So this whole last part from rho squared to the end is just dv. That rho squared is our delta. Now, everything is actually constant limits, so the order really doesn't matter here. I'm going to choose rho first, and then rho goes from 0 out to 2. And then phi next. Phi runs from 0 to pi over 4. And then theta runs all the way around the circle, which is from 0 to 2 pi. So there's our integral. This one works out very nicely in spherical coordinates because all the limits here are constants, which anytime you can get constants here, that makes things a lot easier. So let's go ahead and evaluate that. So starting here, this is the integral we have set up. Well, I took my rho squared times a rho squared to get rho to the fourth. So I can basically pull the sine phi outside of that because I'm integrating with respect to rho. Rho to the fourth, antiderivative is 1/5 rho to the fifth. Evaluate from 0 to 2. So that's 2 to the fifth minus 0 to the fifth, all times 1/5 at the end. That's 32 minus 0 is 32, times 1/5 is 32 fifths, which I bring out front to be 32 fifths here. The integral of sine of phi with respect to phi from 0 to pi over 4 is, well, the antiderivative is minus cosine of phi. And then you want to evaluate from 0 to pi over 4. So that's minus cosine of pi over 4 minus a negative cosine of 0. Okay. Two negatives here make a positive. Cosine of 0 is 1. So I'll write the 1 first. Then I've got minus. The cosine of pi over 4 is 1 over square root of 2. And notice that's a constant, so I can bring it out front of the integral here and multiply it by the 32/5, leaving me just the integral of d theta. Antiderivative there is just theta. From 0 to 2 pi is 2 pi minus 0, or 2 pi. 2 pi times 32 is 64 pi. So we have 64 pi over 5, where the 3 came from. Okay, that's better. And then I have this 1 minus 1 over square root of 2. I'm going to get a common denominator here. First, I'm going to rationalize this by multiplying by square root of 2 over square root of 2. So this is square root of 2 over 2. This is 2 over 2. So that's 2 minus square root of 2 over 2. And that 2 in the bottom cancels that 64 down to a 32. So one way to write it is a single fraction is 32 pi times 2 minus the square root of 2 over 5. 2 is bigger than square root of 2, so this will be a positive number. It's about 11.8. Here it is in a CAS calculator, a TI Inspire CAS. You can see the integration there. They came up with essentially the same thing. If you take that negative and distribute in, you get it the way I wrote it. And then there we get the final answer there. I like my way better, right, because it is a positive number. So anyway, that's a good way to write it in that box, and that box is a probably better way to write it. Approximately, we get that value there. So hopefully that gives you some idea of what we have to do to set up a integral in spherical coordinates, and that gives you an example there. Hopefully now you can practice some of these on your own.